Record. Yeah, I hope so. Okay, so what we had here, I said 64 megabytes, and we're going to break it into 4 banks. So I'm going to have, that means my whole memory is broken into the banks are like the top level. So each one of those would be 64 divided by 4 is 16 megabytes. Megabits. This is a lowercase b. A uppercase b represents bytes, which is 8 times, a 16 megabyte memory would be 8 times as big as a 16 megabit memory. So I got 4 banks. Yeah, and then each one of these has 512 kilobyte subarrays, 512K. So I would need to make 16 megabytes, I would need 32 of them. So times 32 subarrays. Now my 512 kilobit subarray, I'm going to draw a big one here. This is my 512 kilobit. It's got an 8-bit word, which I divide that by 8, which would be 256, would be divided by 2, 128, 4, 64 K bytes. If I did the math correctly, 64K bytes. So I would need to be able to address 64K locations within there. When I address each location, I would get a byte out. So each location would give me a byte. So I've got 64K addressable space. 64K, and I'm done like thinking right now, is 16 address lines. So 64K is 2 to the 16th address lines. So each one of these would have 8 row addresses and 8 column addresses. So I've got, if I think about this whole array, how many address lines I would need, I said it was originally 64 megabits, but with an 8-bit word, which is going to give me 64 divided by 8 is 8. 8 megabytes, which is the number of addresses. This is the actual number of addresses. Okay, 8 megabytes, yeah, is 23.
64 megabytes.
8 megabytes is 23 addresses lines. Address lines. Yeah, because I don't need an address line for every bit in the array. I need an address line for every byte in the array. Because every time I address one location, I'm going to get 8 bits out at the same time.
So it's 64 megabits.
Right.
8 there. So.
Oh, that's a 6.
Yeah, that's what I was saying.
64 megabits. And this is the usual, and I said times 8, but this is just a usual kind of like convention on the data sheets. By 8. What that means is by 8. That means every time I address, it's got 64 megabits, but I get it out 8 bits at a time. So it's really more of a divided by 8 if you're trying to think of this mathematically.
Mm-hmm.
Yeah.
Yeah. So.
Yeah. So there are 8, and so as a total, I've got 8 megabytes that are addressable. And that is going to give me 23 address lines. So how am I going to divide up the 23 address lines? Well, I need 16, the 23 address lines total. I need 16 to tell me which location in the subarray. So which location within the subarray? I need 32 is 2 to the 5th. So I need five address lines to tell me which subarray in the bank and I need 2 address bits to tell me which bank I'm in. So this is how I'm going to divide up my address space. 16 plus 5 plus 2 better come out to be 23. And does it? Yes, it does. So we checked. We've accounted for all our address bits and how we're going to map them out. That's what I really care about more than this nonsense on this slide.
Okay, so 16 locking the subarray, 5 subarray in the bank, and then 2 determining the bank.
Yeah. So I mean, if I could start at the most significant bit, may tell me which bank it is in. Now, the most efficient way to read out this array, though, is to address one row across all the subarrays at the same time. And if I do that, because the row operation is really slow, I can get like a large block of data out, which they call a page or something like that. Just basically, and then just change the column addresses and get a whole bunch of data out at once. A whole bunch of people who do nothing but sit around and mull about how can I get data out faster. Okay. Anybody else? Everybody else is quiet. We talked about the open digit line memory array. If you were given a diagram like this, thank you for annoying me, Dr. Brewer. If you're given a diagram like this, could you identify which is the digit line, which is the word line, where is the storage capacitor, and where is the, wait, no, that's not the digit line, that's wrong. This is the digit line.
Well, it does say what's wrong with this figure.
Yes, that is the shared digit line right there.
Yeah. So,
and these are the capacitors. This is pointing to capacitor right there.
So the circles are the capacitors.
Mm-hmm.
The squares.
See, right here it says this is the digit line contact.
Yeah.
This is the capacitor. I don't know what that means.
What's wrong with the figure? That's what it is.
The active area, okay, the active area is this area right here. That is the transistor. This is the source, this is the drain, and this part of it right here is the gate underneath there. That part of that rectangle.
And the word line is that.
Yeah, the word line is all in poly. It both forms the gate and it performs the function of being the contact between the gates. Okay, we looked at this, and this is kind of gearing towards what we're going to do next in Project 3 for those of you who can't wait. It's already posted. Remember, in the open array architecture, what we did is we pre-charged all the digit lines, this digit line 1 and both digit line 1 star, with the equilibriate circuit to VCC over 2. And then we opened up one of these 1T, 1Cs and allowed it to charge one of these lines up, either up or down a little bit. This other one over here from the second array in your project stays at VCC over 2. So the next part of the project is we're going to take out the equilibriate circuit and we're going to replace it with a sense amp module that has the equilibriate in it, and it has the latch that will act as a sense amp. So we'll have to add more pulse sources for like ACT and NLAT star and IO and all that good stuff. Or you can just tie the IO resistors down. Okay. This is an amazing diagram to have copied on your note sheet. It is literally the answer to one of the questions on your exam. Possibly. I haven't written it, but it's out of my bank of like 10 ideas for exam problems. This is one of them. Pretty much this open architecture, this was the first one they devised. It has a small, it helps you learn how to compare arrays, different architectures. It's got a small in bit, a really low signal to noise ratio, which is a bad thing. High area in bits, you can't twist, and you only need 2 to 3 metal layers. The folded was the next evolution. The in-bit size is bigger. It was worth going to a bigger in-bit size, which means we have a less efficient array, just because our signal to noise ratio was so much higher that we could make probably bigger arrays and things like that and do things more efficiently. Now the thing that they went to, the third thing, was this bi-level that both had a small in-bit size and a high SNR. The only drawback is you need more metal layers. If you can rationally talk about that without this table in front of you, you're okay. If you can write that table down, I appreciate it because it makes grading the exam a little bit easier for me. This is something that you should be seeing on project 2. What you completed today. When I want to access, let's add some signals to this. We'll just do this like a parallel timing diagram. The first thing I want to do is I want to set equilibriate high. And setting equilibriate high charges this digit line right here. This is my output to VCC over 2. I turn equilibriate off and I wait a little bit of time to allow things to settle, and then I turn word line on. Word line has to go up to VCCP, because when I turn word line on, I'm going to lose a threshold across that gate to source, and so I only get whatever word line voltage is minus a threshold for my charging voltage. So this goes all the way up to VCCP. As soon as the word line goes on, the entire row of transistors turns on, and these capacitors dump their charge onto the output. And remember, it's a small capacitance here. It's a big capacitance here. So I only get a small amount of charge if this is a 1. If D1 is high, I get a small amount of charge going out onto the digit line. The next step would be to turn on the sense amp, but we skipped that part on project 2. But I turn on the sense amp and I would take that and it would go all the way up to VDD, my output. Now, after that, after I'm done reading out the array and I've got it through the sense amp and I can send it out to the rest of the array, my next step here would be over here in time. I turn the write enable on. And the write enable allows me to write a 0 or a 1 into the cell. As soon as you read a DRAM cell, you've destroyed its memory storage capability, because the memory was stored as charge, and that charge has been used to charge up the line, so it's gone. Okay. If D0 was low, it actually comes down faster. This isn't a typo. It does come down as you cross the threshold voltage of that transistor. It starts coming down probably right about there. That's the threshold. And pulls it down a little bit, or it pulls it up when it's reading A1. This part you probably saw on your project if you're paying attention to the timing. The problem with the MBIT, it's a tiny little capacitor because we're putting it in like a 9 nanometer squared area, or 9 nanometer, 81 nanometers squared, 9 nanometers by 9 nanometers. So it's a small capacitor. If it's full of charge, and this is pre-charged to VDD2, when we open up the valve or turn on the word line transistor, this is only going to go up a tiny little bit. And if it was empty, this line would only come down a tiny little bit. So that's why we need the sense amp.
Judging from the output of the lab, it's actually more of a jump than I thought it was going to be.
Yeah, it's going to vary. You want to know how you make it smaller?
I mean, you just make the entire thing smaller.
Right.
Or add more.
Okay. Here's the problem. You've got like a 25 femtofarad capacitor in the MBIT, right? Okay, that's huge. Now, that's maybe like 30 nanometer days. Now, we go down from 30 nanometers to maybe like where they're at now, which is like 8 to 9 nanometers, and they're probably pushing 6 right about now. That 25 femtofarads goes down to maybe like 5 femtofarads.
That's a big jump.
And then so your voltage shift is going to go down by like a factor of 5. So the way you can be the hero and get the cell size down and still be able to read it is you design a bit better sense amp. And that is what they've been doing a lot of work on that, trying to get more and more sensitive sense amps. It's no longer a latch from what I understand. Their current iteration is it's an op amp.
Interesting. So long as they can make the op amp small enough.
It's small enough to fit in a 2-column pitch. They have to make it narrow, and they can make it long.
Baby op amp.
Yeah, the real extreme on this is when I was at JPL, we had to build a 10-bit ADC, and it had to fit in a 15 micrometer pitch. And it was about a centimeter long. We could go as far as we wanted to in the other direction, but it had to be like this narrow because we had 1,000 of them on one chip. It was on our readout, basically our column. Instead of reading out a digital value from our imager, we read out an analog voltage that represented how much light we had there. We'll talk about that when we get to imagers. A lot of Julie's history of the universe there. So we talked about this diagram in a lot of detail. And well, we've already gone through that. We're down here. So this charge sharing, if you want to actually calculate what your predicted shift up and down is, you can do that by estimating, first of all, if you know the actual value of C MBIT for your process, and you know how many femtofarads per nanometer your digit line is going to be, and you know how many cells you have on your digit line, you can calculate C digit line. And what you're going to get here, this node is initially charged to VCC over 2. This is our pre-charge side of it. When I turn the MOSFET on, I'm going to throw this switch down and close the switch. I'm going to have some final voltage across there. Now, what the signal voltage is the difference between the initial voltage and the final voltage. That just tells you how much signal you're going to get on the line. And then you would have to add or subtract that from VCC over 2 to get the final voltage. Okay. And notice there was a whole bunch on the front page of the exam. There was the numbers you got were all about capacitance.
see.
You see. Okay, is that enough of a hint for everyone?
And definitely write down these equations.
Write down these equations and understand. Oh, and really, trust me. Trust me. Understand the initial voltage over here is VCC over 2. So the final voltage is VCC over 2 plus, or, you know, whatever it is, plus VSig. And VSig may be a negative number. This is how you calculate VSig. Okay, and there was a homework problem on that too. You may want to go back and review that. Yeah. A lot of the material from the exam, kind of the real meat of this is really coming from the ideas that are making it onto the project, and a lot of that's in chapter 2. This is a sense amp, and if you look at this piece right here is an inverter, and this is the input of the inverter here. And this is the output of that inverter. So I've got an inverter with an input and an output. The output of that inverter goes into the input of the other inverter. Yeah, a latch. And then the output of that goes back into the input right there. It's a latch. It basically stores the value that's on there. What we'll get to in project 3 is what this ACT and NLAT star are. Is ACT is the positive power supply for this inverter, and NLAT star is like the ground. But we're going to switch those on and off just to confuse you. And we got into a wonderful problem that Corey and Sean figured out last semester or last spring. So here we go. This is the sensing operation. We're adding a little bit to the timing. And there is one big ugly timing diagram on the exam always. We pre-charge to VCC over 2. Word line comes on. I get a little bit of extra charge on my digit line. And then it's really important here when you do this that you make NLAT come down first, then ACT comes up, because the lat, if you do ACT first while NLAT's at VCC over 2, the latch tends to latch at VCC over 2, which is also a stable state. So don't do that.
So what is that extra line again that goes up slightly?
The one, which one? Oh, the one that goes. This is the output.
Okay, that's the output.
That's the digit line output. It goes up slightly, and as soon as I turn on the sense amp, that little bit of difference between that and the other input pulls it all the way up to VCC.
Dip slightly.
Well, yeah, I don't know how accurate the dip is for whatever technology you're using. So I know the NLAT and the ACT thing is real because both Corey and Sean proved it to me.
I can't remember when Corey was really excited about that.
Okay.
He was just, yeah.
Yeah. This is the sense amp that you will need to build for project 3. It's got a latch. It's got 2 P latches. These are the P sense amplifiers because they're PMOS. The N sense is right here. N sense. The equilibration circuit is the one that's labeled EQA and EQB. It's just two halves of it to make, if one of them fails, the other one will work. That's one reason for that. The other thing is you get a little stronger, a little faster signal with having 2 of them in there. The IO transistors are right here. They're labeled IO. And the isolation transistors are right there. Okay. You may see that diagram on the exam, along with, yeah, so you might see something like this on the exam. If I pick a point in time in here at random, can you tell me what's going on what the signals are. Like, let's take word line. Word line right here, this the WL, what is it? And the first correct answer is word line. The second correct piece of this is, well, it's at VCCP. So because we lose a threshold across the N-bit transistor, and that is indicating that the N-bit transistor is on. And this allows you to both read and write to the cell. Can you tell me a little bit of stuff that makes sense about each one of these signals? Kind of describe all of these signals in here. DLAT, ACT, with the C-select, yeah, ISO. Yeah, just kind of describe the signals in there. Did somebody, I didn't know it was me. No, nobody's chatting. So given a point of time, can you tell me what's going on? Okay.
For example, like that point with the NLAD, let's say you say the amplifiers turning on.
Yeah, so inlet going down and ACT going up. Where's ACT? ACT's going up and inlet's going down. That indicates you're powering up the sense amp. That would be an amazing thing to say about that. If you generally, I don't, when I look at paragraphs that engineers have written on the fly during an exam, what I'm looking for is perfect doesn't necessarily mean you match what my answer is. The first thing I do is I read your answer and I see if it makes sense. And would it embarrass me if you said this in front of another engineer, in front of any Micron employee? So those criteria of does it make sense and would it embarrass me give you a lot of points right there. Whether there's a complete explanation or not of what's going on, and it might be slightly different from mine. It's just basically I'm looking to see how you're thinking on the fly. And if you just say word line, or you say WL, word line, it's high, you're not going to get full credit for that. I want some kind of explanation for what this means to you. How does it make you feel?
How does it make you feel?
That word line went up.
Make me feel sad.
It was like the question my son hated the most in high school. And the part of my whole high school curriculum he absolutely hated was poetry. How does it make you feel? And the poet he hated the most was E.E. Cummings. So I heard a fly and then I died.
What is the D0 signal doing on the last?
Oh, yeah, D0. Okay, D0 star. So D0.
D0.
Oh,
D0 star makes sense to me.
Okay, D0 star is actually like, remember there's two sides to the sense amp. Sometimes you're reading data on the star side, and sometimes you're reading data on the non-star side.
They're not necessarily.
Right, because there's only one sense amp for each pair of columns.
So when D0, whether it's D0 or D star,
Right.
D0 star,
Right.
When it gets, it's just saying when it goes high, it's
Right.
reading data on it.
Right. And D0 is just the other side that's not being read.
Which for some reason changes.
It's once you get into the right cycle, it's going to change because you're actually forcing. Once this D0 star goes up, D0 star going up right here is going to cause D0 to dip down towards ground. And then when you start writing, so when you get to like to the end of the write cycle, D0 is still D0 star not. It looks like you're writing a 0 here.
Mm-hmm. So you're writing a 0.
You're reading a 1 and writing a 0.
Yeah. Because so D0 star is
right. Right.
And D0.
And whenever you force D0 star down low, you're going to force D0 up.
What is the isolation layer doing there when it goes high?
The ISO, okay, the ISO is part of the readout. ISO, we'll get to that later. Okay, so let's start talking about the IO transistors first. The IO transistors, what they do, they determine if the output of this particular sense amp is going to go into the, it's kind of like the demultiplexer end of it. They determine which sense amp output is actually going to be read out as being valid, as being data. Because once I turn the word line on, all those sense amps activate. Well, everything on that column will activate. All the yeah, a lot of, okay, so once I turn the word line on, every column on that word line is going to dump its charge out. We're going to power up the sense amp on a particular column. But you have to be able to regulate which one of those sense amps is actually going to send data out to the output buffers and things like that. So that's what those what those IO transistors are for. The isolation transistors are going to be more used, I think, in our project. Basically, we just leave them on all the time. But if this was a dead array, I may want to isolate this array from the other one and just turn them off permanently. Or if there is a problem with that array or something like that.
Okay, so when since it starts, since ISO starts low.
Yeah.
It starts low, but then later goes high.
And it's going high. So when it goes high, we're going to turn those transistors on.
Okay.
Yeah.
So it's just the ISO transistors turn on.
The ISO transistors turn on. And then that's actually allowing the P sense amp and the N sense amp to talk to each other too. Okay, so there's a whole lot of, yeah, sometimes, yeah. Okay, the word line drivers, pretty much, we talked about these. We have to be able to drive the entire capacitance of the word line, so we need a big drive capability. We also have to drive it higher than VCC, so we need this bootstrap driver to drive it to a higher voltage. Okay. Basically what I'm looking for here, if you see a schematic like this on the exam, do you know what this means? Could you make a truth table for it? If I gave you all the values for all the input signals, could you tell me what the output signals are? Yeah, this is 110 stuff. Okay, this is 380 stuff. If I gave you this schematic on the exam and I asked you to make a truth table for it, could you?
I need a refresher.
Yeah, basically the thing is that this is dynamic logic, so you'd have to look. Oh, good. Something's wrong here. Touch, don't touch. Okay, and then it's, I don't know why it won't let me draw. Am I in white?
No.
Okay, it's, I don't know, but it won't let me draw on it. The big thing you'd have to look at, I can draw my finger if I touch. Okay, so I'll draw with my finger. You'd have to look at pre-charge. There would be two states to this. When pre-charge is when pre-charge is low, and I can't, okay, pre-charge low. If pre-charge is low, my output, this output is high no matter what. If pre-charge is high, sorry, I'm finger painting. No, it won't let me draw it all. Oh, I'm frozen. Okay. So, and if pre-charge is high, then it's going to evaluate based upon RA1, RA2, and RA3. It's domino logic. So if you saw that schematic, would you be, or dynamic logic, would you be able to kind of analyze what's going on? There's a little bit of feedback here too. If DEC is high, this transistor turns off.
Because that's an inverter there with M5.
Right, so this would have to be low. Yeah. Okay.
Yeah.
It's just basically, probably, oh, I know what M7's there for. M7 is so you don't lose a threshold. Okay, and we'll come back shortly. I'm gonna reboot.
Like the start menu or anything?
What?
You can move the mouse.
I can move the mouse.
You can't click start or anything.
Can I click start? Where the heck is that?
This key?
Spacebar on the bottom.
No, it doesn't do anything. It just gets the little, okay.
Are you able to pull up task manager?
Control Alt Delete. No, because my screen's frozen. I might be able to do it, but my screen's frozen. I can't see anything. So I'm just gonna hit this. I'll see.